helium 3 reaction channel and an alpha deuteron reaction channel. Those are the two-body reaction channels, but those would have a very high centrifugal potential to go through, so you wouldn't expect it. And in fact, at least by observations by Kasabi, there's no evidence for these two-body channels, which is actually quite strong support for the presence of high angular momentum if these things in fact are compact states. Conjecture: compact two-deuteron states that exist are high angular momentum states where high means on the order of 20 or larger. Let me talk a little bit about the theoretical foundation. And at this point, I probably have to begin carrying sleeping people out of the room. But in the nuclear physics community, the early description of fusion reaction processes was done through something called the resonating group method. Wheeler formalized the resonating group method. I suspect he invented it as well, but I'm not sure of that. Basic idea is that you make a wave function that has pieces that describe the nuclei, and then a piece that describes how far apart the nuclei are from one another. You assume that the nuclei are fixed, and you try to get the very best approximation for the description of their dynamics. And to do that, you take your trial wave function, you put it in your Schrodinger equation, you try to optimize the channel separation factors, and you get what's called coupled channel equations. And these equations are what the nuclear physicists use to describe DD fusion processes from the 1930s till the early 1990s or so. This competes with the closely related R-matrix method, for which everything I'm going to talk about carries over. I'm proposing the lattice resonating group method, and the basic notion is that you'd like to include the lattice at the outset in your theoretical description. So the proposal is to start out with a wave function that's constructed similarly. The nuclear pieces will be the same as we had before. The only difference is here, instead of having just the two-body channels, let me include the rest of the lattice as well. The two-body channels include center of mass coordinates. The center of mass coordinates can be chosen for all the other nuclei as well, and it costs nothing extra other than massive amount of complication in your channel factors to generalize the normal nuclear vacuum description to the lattice. So this is it. This is proposed in 2000. The optimization of the lattice channel factors is done in exactly the same way as for the normal vacuum problem. And this gives you the theory. This is the content of the foundations of the theory that I'm using to work on the anomalies. So if you'd like to believe that there's errors in it, this is the place to start pounding on to look for problems with it. Postulate: new physics must result from correct quantum description of both the nuclear and solid state systems. The proposal that I'm making is just simply to combine them. Take your best nuclear description, your best lattice description, combine them together. Time's starting to run short, and I'm starting to get into theory, so I'm likely to, I think it's probably appropriate to do a bit of fast forwarding to focus on some of the conclusions that are important. I proposed a two-site problem as being the simplest possible version of this that you could analyze. And the two-site problem would have helium-4 on one side, two deuterons on another side, all deuterons, all helium in exchange. So you can set up the channels for this problem, and you can work through absolutely everything if you assume simple nuclear models. You still have to deal with the interaction of the lattice with the nucleus, and this is non-trivial. The proposal is that a coordinate for the center of mass of the nucleon, you've got, if you're doing a nuclear problem in vacuum, you care about where the particles are. So the center of mass coordinate is important. If you're in a lattice and you have a highly excited phonon mode, well, the phonon mode is important, and you need to describe that properly. The proposal is to include the phonon mode as well. And whatever's left over basically is a residual local coordinate. So in this way, was proposed as a way to analyze the interaction between nuclei on a lattice in the presence of a highly excited phonon mode. If you do this, you actually can analyze and get an analytic expression for Gaussian interaction with Gaussian orbitals for your interaction, which tells you everything about how phonons are exchanged and angular momentum is generated in these reactions. This has been, for this problem, this has been analyzed and understood completely. We generate a couple channel equations, lots of them. So the thing about this formula is that you get lots of coupled equations. And you solve them all, and what you find is that the two-site problem does not give a stable two-deuteron compact state. So you go through all of this, and at the end it says, it doesn't work. And the reason it doesn't work is that the coupling's not strong enough. And then you've only got one site to exchange with. So brainstorm was if you included other sites, and many sites, that the interaction would be stronger. Which has been done. Now, in order to try to get a handle on what things would look like if you included more sites, I made use of something called the infinite order Brillouin-Wigner theory, which is in nuclear physics, the projection operator version is also known as Feshbach theory, the Hermann Feshbach, formerly of MIT. If you use infinite order Brillouin-Wigner, you get something like this, and this reads molecular D2 problem and other stuff. And this other stuff reads, take two deuterons, have them come together and make helium-4. Have the helium-4 come apart at another site and give two deuterons. So it's an exchange term. The question is what if you take something really complicated and you want to understand it, you make a simple analog. So a simple analog in this case is a one-dimensional well, which represents the molecular D2. An exchange term near the origin, which represents this new process. And this gives a problem that you can solve exactly. And the claim is that by solving exactly this simple problem, it tells you something about the behavior of the very complicated multi-channel problem described. Now what this simple problem gives, when I saw this, I was stunned because I didn't know it was possible, is that this simple problem gives a compact state. It gives a real life new state. Well, it's not a new state. Your Hilbert space has to stay the same, but the states that were present previously combine to give you a localized state. You have a localized state, the energy of which depends on the coupling constant for the exchange potential. These states here are the normal bound states for the well, which represent the molecular ground state versus excited second excited state. But this new thing here is a compact state, which is localized near the origin. The one-dimensional analog then, in fact, gives what you can identify as two deuteron compact states in the problem. Now, if you look at the molecular state now with this exchange thing, in this case I've chosen to do a reasonably realistic molecular D2 potential problem. What you find out is if there's no exchange, you get a wave function that looks like this. But when you start to turn the exchange on, then your boundary condition changes, and when your boundary condition changes, you start to get a different behavior near the origin. And what this means is that in the presence of a compact state, which is nearly resonant with your molecular state, the probability that you can go from here to a small radius now changes dramatically. And that is very, very interesting, because there's always been a problem of how you get two deuterons close together, given that tunneling inward is inhibited. Well, the answer is if you have a compact state, your resonant small r, that changes the boundary condition, that changes what the state looks like. So compact states in your resonant changes the probability. Okay,